you said, is cosmological radiation density with non-standard neutrino-electron interactions and how this can be related to Lorentz invariant violation. So the first idea I wanted to talk about is the fact that non-standard interactions modify how neutrinos and electrons interact in the early universe, and this affects how neutrinos are coupled from cosmic plasma. And forthcoming CMB observations are gonna perform very accurate measurements of observables related to this process, and hence we can use it to constrain these non-standard interactions. And when I say forthcoming, I mean by the end of this decade, beginning of the next decade. So it's really not too far in the future. It seems reasonable to talk about this. So first, to just put the whole thing in context. So I'm going to explain quickly the process of neutrino coupling. So in the early universe, at temperatures larger than 1 MeV, approximately, neutrinos are tightly coupled to the cosmic plasma through interactions with electrons, which at the same time interact with photons. But at some point, for a temperature around 1 MeV, weak interactions stop being effective, and so neutrinos effectively decouple from the rest of the cosmic plasma, and they evolve freely, whereas electron, positron, photon plasma is still coupled. And then again, when the temperature reaches around the mass of the electron, then the process of pair production of electron positron from 2 photons is no longer possible, and then there's only this channel, so electron positron annihilation with photons. This means that there's an injection of entropy into the photons, and that increases the temperature of photons with respect to neutrinos. So this is basically the idea. The whole process actually is like more complicated, because first, it's not that weak interactions stop working at a certain temperature. It's a process. So it's not just that it stops happening. Also, you have to remember that, for instance, electron neutrinos scatter with electrons via neutral current and charge current interactions, whereas a scattering of muon and tau neutrinos with electron only happens through neutral current. That means that even in this instantaneous decoupling picture, muon and tau neutrinos do not decouple at the same time as electron neutrinos, but then one also has to think that neutrinos oscillate, so it's a complicated process. And similarly, electron positron annihilation is also not just an instantaneous process. And to make it even more complicated, these two things overlap slightly. So the computations are complicated, but the overall pictures, I hope it's kind of clear. So first, weak interactions, and then stop working, and then we have electron positron annihilation and raise the temperature of photons. So after all this has happened, when the temperature is smaller than the mass of the electron, then the cosmological radiation density can be written in this way. So it's the sum of the density of photons, the density of neutrinos, and eventually one could have some other relativistic species and some BSM extension that you do of your standard model. But for the moment, I'm just gonna neglect that. So basically, the radiation density is the density of photons, and then the contribution from neutrinos that is written like this. So this term comes from the fact that they're fermions. This is related to the ratio between the temperature of neutrinos and photons. And then we have this parameter called N effective, which is the effective number of relativistic species. So one would think that since we have 3 active neutrinos, then this number is equal to 3, and that's it. And actually, in this instantaneous picture that I presented at the beginning, it's exactly 3. But as I told you, it's not so easy. So there's some deviations in the standard model from this exact number of 3. This is due, as I said, to the fact that there are non-instantaneous processes. Also, we have neutrino oscillations, which also generate a small deviation from 3, and finite temperature QED corrections. But these things can be taken into account. 2 different groups did so, and this is the most recent calculation that can be found in the literature. And you can see this tiny error, which is basically due to the uncertainties we have in the measurement of the oscillation parameters. So actually the theory is clear, or the theoretical frame is clear, And the main contribution to the uncertainty is actually coming from uncertainties in experimental data. So this is actually quite good. And the idea is that if one ever finds a deviation from this value, it means that either there's an additional relativistic degree of freedom, or there's new physics in the neutrino sector, apart from oscillations, which we have already accounted for. And so we wanted to study one of these new physics scenarios, and we focus on non-standard neutrino electron interactions. So now I'm going to talk about that. So we will be focusing on neutral current non-standard interactions with electrons because they're the ones that have a larger impact. So these non-standard interactions arise in many mass models and be understand model extensions, and that's why it's interesting to study them. And so they can be parameterized in terms of an effective Lagrangian like this one, where I have introduced these epsilon coefficients, which are dimensionless, and they quantify the strength of the new interactions with respect to the standard model ones, in the sense that when this coefficient is equal to 1, it means that the non-standard interaction is as strong as a standard model interaction. They can be separated into two types. So first one are non-universal NSI, which do not produce a change in the flavor of the electron neutrino, but if two of those are different among them, then that means that a flavor universality is no longer present in the model. And there are also flavor changing NSI, which actually produce a change in the neutrino flavor when scattering with an electron. And so having these new interactions modifies how we do neutrino physics in two ways. So the first one is because now when neutrinos propagate in matter, they feel an additional interaction. That means that neutrino oscillations are modified to an effective potential. So the same way that standard model interactions produce an effective potential that gives rise to matter effects, then NSI would do the same. And the whole picture also changes because now cross sections that we use for measuring neutrinos also change if the cross section involves the scattering of neutrinos with electrons. And so by studying these, bounds on these non-standard interaction parameters have been derived mainly from such oscillation experiments and scattering experiments, also when combining with some lab observables. So we actually have already some studies on this. So you can see this recent review for a better explanation. But what we want to study is how NSI alter the decoupling and the impact that they have on the effective number of neutrinos. So this whole picture of the coupling changes, as I said, because the oscillations are modified. They actually, for what it concerns us, this modification is very small. It's a subleading effect that we could have even ignored because it's well below what can be experimentally accessible, but still we accounted for it just in case. And the main contribution comes from the interactions that keeps neutrinos in thermal contact with the rest of the plasma. So now we have extra interactions of neutrinos with electrons. That means that if, depending on how these interactions are, neutrinos can decouple earlier or they can decouple slightly later, and this leads to a different value than effective. So by measuring an effective, we can actually get information on this NSI parameters. In a practical way, what we see is that the standard model coefficients are shifted in this way. So in the cross sections, whenever one has GL, in the presence of non-standard interactions, one have to substitute by this combination, same for GR and the product GL-GR. So you can see these are non-universal NSI, and they can, depending on their sign of this parameter, they can either enhance the value of the coefficient or reduce it, whereas flavor changing NSI can only lead to a higher value. And we'll see this impact just in a few slides. At this point, I want to make just a few technical comments. So computing, this is complicated. We have to solve Boltzmann equations in an expanding universe, also using a density matrix formulation in order to account for neutrino oscillations. So it's quite heavy computation. I will skip all that part. We took the oscillation parameters from a recent global fit, so you can find the references down here. And we want to compare these to the forecasts for future sensitivities. So for you to have a taste of what's currently going on, Planck measured an effective to be around 3-ish, plus minus 0.2, more or less, depending on the data sets that one combines. But the sensitivity is more or less at the point of 0.2. For future surveys, one has Simon Observatory, which is expected to improve that limit by a factor 3 or 4. And then CNPS4 project, which could actually improve it in one order of magnitude. So that means measuring an effective with a precision of 0.02. And this is actually very good. So now I want to show you how this effective varies with the different type of NSI parameters. So let us first see what happens with non-universal NSI. As I said, they can cancel out the standard model interactions. That means that there are less interactions between neutrinos and electrons in the plasma, so that neutrinos decouple earlier, and that leads to a smaller value of an effect. Conversely, these NSI parameters can also enhance the interactions that one already has. That means that electrons and neutrinos are more tightly coupled. They will decouple later, and that leads to a larger value of an effect. So in this plot here, you can see how an effective changes for two different parameters, epsilon tau tau and epsilon EE, so the left-handed coefficient. The color bands represent 90% confidence level bounds derived from terrestrial experiments. And the shaded gray area is the projected sensitivity for CNPS4 project. So let's have a look at what it looks like. So you can see, for instance, there's a minima in an effective here and here, which actually corresponds to the value of the NSI coefficient that cancels out the contribution from the standard model to the cross sections. So this is exactly what we expected. And then you can see that for some values, we get a value of an effective smaller than the standard case. That's when NSI, so non-standard interactions, are canceling out standard model interactions. And we also have regions in which the interactions between neutrinos and electrons are enhanced. Flavor changing NSI between electrons and neutrinos are not present in the standard model. So if we have this extra interaction of this type, that means there's the interaction rate between electrons and neutrinos is larger, and that leads to a delayed decouple of the neutrinos. And consequently, we see always a value of an effective larger than the nominal one expected in the standard model. So again, this purple band is the limit from terrestrial experiments, and this is the sensitivity expected for CNPS4. One can go one step beyond and see what happens when one varies two parameters at a time. And so in this plot here, you can see isocontours of an effective. So for these choices of this combination of NSI parameters, so this is what the value of an effective will be. In white, you can see the shaded areas are terrestrial bounds, and this point is the standard model prediction. So if you take this, as I said, this is the standard model prediction, and the sensitivity of CNPS4 is 0.02. That means that at one sigma we will be able to determine like something like this area here. Okay. So you can see it's really not that competitive with the terrestrial bounds we already have, but it's good to see that soon in the future, cosmology is actually going to be able to test this. I want to show you another combination. This one is particularly interesting. So epsilon tau tau and epsilon e tau. So again, these are isocontours of an effective, and the interest of this is these two bounds have been derived separately, so in different experiments, and there's no way on Earth to prove these two simultaneously. But actually cosmology can. So even if the bounding from cosmology, it is the area enclosed by this ellipsis here, so even if it's not as good as the terrestrial bound, it's true that these terrestrial bounds were obtained varying only one parameter at a time, whereas this is a multi-parameter fit. So actually, cosmology is sensitive to possible interplays between these two NSI interactions. So in this sense, cosmology is competitive with terrestrial bounds. So that was the first idea I wanted to talk about in this talk, so that in the future, non-standard interactions can be proven from the fact that they modify the decoupling of neutrinos. And now I also wanted to just quickly talk about the interplay between non-standard interactions and Lorentz invariance violation in the framework of the standard model extension. So this is a Lorentz violating extension of the standard model, which keeps the symmetries of the standard model. And we are going to focus on CPT or renormalizable terms, like these ones here. And actually, I'm just going to focus on a particular combination, which is here, because it's the one that's actually relevant for left-handed neutrinos. So it's a combination of this parameter A and B, which I call AL. From now on, I'm actually going to drop the L, just to keep the notation easier. And I'm going to focus on the index 0, because non-zero mu1, 2, and 3 will break rotation invariant. So I just want to focus on isotropic components of this Lorentz invariant violating terms. So when one accounts for this terms, one finds an effective Hamiltonian of this form, which if you're familiar with NSI, will see that you will immediately notice that it's formally equal to the effective Hamiltonian that arises from non-standard interactions, which is written here. So you can basically see they have the same form, but they're completely different conceptually, okay? Because NSI are like an exotic form of matter effect. So it's only present in propagation matter, and it changes if the matter density changes. Whereas the effect coming from this Lorentz invariance violating parameters are present always, even in vacuum, and do not change with the density. So conceptually, they're different. Nonetheless, it's possible in some cases to translate the bounds from one to another. For instance, if the bounds derived on NSI happen to be on certain conditions on the matter density, for instance, on an almost constant matter density, then this term is basically constant, and one can actually identify the terms quickly and translate the bounds from one thing to another. But this is a small disclaimer. This can only be done with the bounds on NSI are derived in propagation. So bounds on NSI from scattering cannot be translated. This means that the bounds that we have derived from cosmology, which are based on the scattering and annihilation processes that keep neutrinos in thermal contact with electrons from the cosmic plasma, cannot be translated into Lorentz invariance violating bounds. This is, okay, it's not as good because we would like to have actually on some Lorentz invariance violation from cosmology, but there's one positive side to this. Whatever bounds we derive from cosmology, they're robust against Lorentz invariance violation in the sense that one could never argue that there's an interplay between Lorentz invariance and NSI that cancel us out, and that's why we don't see new physics. The bounds derived from cosmology are robust, and they're not affected by this type of Lorentz invariance violation. So this is quite a positive message. And just my two take-home messages. The first one is that we're reaching a point where cosmology is actually going to be able to set competitive bounds on neutrino properties. In particular, I talked about non-standard interactions. And the second important thing is that these bounds, since they're based on scattering, they're robust even in the presence of Lorentz invariance violation, in the sense that we're going to be able to test separately both effects. And so that is it. Thank you very much again for having me, and I hope you enjoy it. I'm happy to take questions if there's any.
Very nice talk. We have quite some time for questions. Are there any questions in the audience? There's one.
This should be relatively quick, but I think at least I didn't see in the talk. What are the current, what's the current precision in the effective N cosmology, and how much is it expected to improve?
Sorry, can you repeat the question? I couldn't hear very well.
So what are the current precisions in N effective from cosmology?
I'm really having a lot of trouble to understand the question because it like the audio gets cut sometimes.
I think they're going to write in the chat.
Yeah, maybe if you could write it, that would be great.
So what's the precision in effective from current experiments?
I'm really having a lot of trouble with the audio. I don't know if there's something I can do. Could anyone type it in the chat? Okay, thank you. So the precision in current and effective measurements is 0.2. So it's expected to be improved by 1 order of magnitude. So currently, this NSI effects can barely be tested. Like one can actually get bounds, but one gets bounds of non-standard interactions being 1 order of magnitude. I mean, 4 times. So from cosmology, we know non-standard interactions are less than 4 times the strength of the standard model interactions, but like that we already know. I mean, we would have a problem if non-standard interactions were so large. So current limits are not competitive. They're going to be improved by 1 order of magnitude. So from 0.2 to 0.02.
There's another question.
Yes, these non-standard interactions will affect also the electrons because of gauge invariance.
I'm sorry, but I'm gonna have to ask you to repeat the question, please, because really I don't know what can I do about this audio.
These non-standard interactions do not affect electrons also because of gauge invariance. They are not translated to electrons.
In principle, we're being agnostic about that. So they just affect interactions between neutrinos and electrons, but they just affect that. So in principle, once they decouple, it's okay. Like it's just non-standard interactions between neutrinos and electrons. That's the only part we consider. We didn't consider non-standard interactions in electrons or among electrons and other stuff for neutrinos and other content of the star model. We just focus on that because that's the part that affects most the decoupling process. I don't know if that answers the question.
Are there further questions? Okay, I don't see any further questions. So thank you for the very nice talk.
Okay, thank you very much.
Saeed Rastgoo. Hello, can you hear us?
Yes, can you hear me? Hi.
Yes, we can. So you can share your screen?
Yes, 1 second. Can you see my screen now?
Yes, we can see your screen. Okay.
Sorry. Yeah.
Our next speaker is Saeed Rastgoo from York, and he will talk about non-perturbative quantization of gravitational waves model. So please.
Thank you. So thank you first, the organizer, for organizing this workshop, this conference, and also giving me the opportunity to present this talk. So this is a work based on our recent paper, which is actually part of a chain of papers which appear in future soon. The idea is to non-perturbative see if we can get some information from gravitational waves regarding the non-perturbative quantized space-time And by extension, if a spacetime is quantized, most probably the gravitational waves should, be kind of quantized and show the signs of or signatures of those quantizations. So what we did at the present work is just quantization of the gravitational wave that are propagating on a classical spacetime, but nonetheless a classical FLRW spacetime. In future, we will turn this into also the spacetime background should be quantized, and we are in the process of doing that. So the classical setting, let me start. I start by giving you the theoretical background, and then I go to the results. So the starting point basically is Einstein-Hilbert action. You have some background metric, which we take to be the G naught, take to be the FLRW cosmological background, and the perturbations, of course, are gravitational waves. So this A here is the scale factor. You know all of these things. So we choose a certain gauge, which is usually taken in gravitational waves, which is called synchronous transfer stressless gauge. See that trace of H is equal to 0 and 0 mu component equals 0. Divergence of special part with respect to the background metric is also 0. So in this gauge, we can decompose the perturbation that you saw before into plus and cross polarizations. And each of these polarizations, these components here, H plus and H cross, can be written, we write them in Fourier form. As you see here with these curly A's here, these are the Fourier components of H, the perturbation. And this A comes with a polarization and a mode. So sigma is the polarization plus cross, and K is the mode. This L is basically the length of the box we are choosing to quantize, or you can think of that as the bound on the momentum of the whole system. The conjugate to these A's, curly A's, are these curly E's, and these also hold these sigma and K indices. As I mentioned, so these A's are configuration variables, Q's of our canonical formulation, and E's are our momenta conjugate to curly A's. Now, having these all, we can go forward and compute the algebra. The algebra happily becomes, as you see here, the delta. Because we're choosing the box quantization, basically these deltas are not Dirac deltas, these are canonical deltas. Next is to write the Hamiltonian. So the Hamiltonian for the whole system becomes like this, where A is the scale factor, N is the lapse, and this part is just the Hamiltonian density if you want. So you see the Hamiltonian is also mode dependent and polarization dependent. And these are all the information that I mentioned. So as you see, the Hamiltonian looks like a set of decoupled harmonic oscillators that each have a mode K. However, this harmonic oscillator that you see each of these, the frequency A here, or basically K A squared, this is a time dependent frequency. So you will see that this poses important obstacles in quantization, but we will kind of go around it by some certain canonical transformation, as I mentioned. So here's the Hamiltonian that you see here. We choose a harmonic gauge where our lapse is just a scale factor cube in this time that is associated to the harmonic gauge, and this is our H at the end using the harmonic gauge. Okay, so as I mentioned, the Hamiltonian that you see here is a Hamiltonian with a time-dependent omega. Now, if you want to go ahead and quantize this, we quantize this using something related to quantum gravity. It's called the Polymer Quantization. I will talk briefly about that. But if you want to quantize that, no one really knows how to polymer quantize or a system with time-dependent or harmonic oscillator with a time-dependent frequency. So what we do is, as I mentioned after this slide, let me just briefly explain what is polymer quantization. So in loop quantum gravity, you have a formulation based on connections. So instead of metric, you use connections like other fields of nature, is the electromagnetic U1, the other weak SU2, and the strong SU3. In loop quantum gravity, use connection. This connection is called A, or Ashtecar-Barbero connection. Now, in quantum theory, so in classical theory, we use the connection, but then we change the formulation. And here's the important difference between loop quantum gravity and other approaches, is that we don't use A, actually, the connection itself. We use the holonomies of A. And these holonomies of A, you can see, you can notice that classically, based on some theorems, having the holonomies of all the loops in a space-time, basically it's like path order exponential of a loop, integral of a loop of these connections. So if you have all information of all of them, you will have information of the Riemann tensor, and basically they're equivalent. This is equivalent to the general relativity classically. But when you go to quantum mechanics, then it turns out Hilbert space of loop quantum gravity is such that the A itself does not exist. Only the holonomy exists, like some sort of exponential of that exists. And this leads to all sort of different results, because the Hilbert space is now unitarily inequivalent to usual Schrödinger representation that you use in all sort of field theories around. And obviously the physical results will be different, and singularity resolutions come because of these sort of different Hilbert space. Now, long story short, in order to find an effective Hamiltonian based on this quantization, all we have to do in this case is just, it's equivalent to quantizing and blah, blah, all the way, go to act it on some state. But the equivalence is that you just change your variables, like in this case A, or in Q in your Hilbert space, to sine of delta A over delta, and this delta is something called polymer scale, and this basically sets the minimal scale of the theory, where quantum gravity effects should appear close to that scale. Okay, so let me actually pass this slide. So in this case, in our case, we have to change Q to sine of mu, Qj over mu. And this is the essence of polymer quantization. Okay, so because of the time, I will just pass that. Remember that I was here, so I mentioned that it's not easy to polymer quantize a time-dependent oscillator system. And what we do here, if we go to the polymer quantization, now we make a trick. So this is the trick here. So we start with our Hamiltonian that we saw before, which is written in terms of curly A and curly E. These are Q's and P's. We go up to the extended phase space in the sense that we take our time, t parameter, and its conjugate momentum, pt, which is basically related to the energy. We take that and we enlarge our phase space. Okay, so this is the first step. In the second step, now we will have this action in the enlarged phase space. So this is the original. So this is the extended phase space. This is the new action in the enlarged phase space, and this phi is our constraint, which makes sure that pt is equal to Hamiltonian. And you see we have added p dot q, like pq dot here is another, t is another q in the enlarged phase space, and this is our Hamiltonian related to the pt. And the next step is we do a canonical transformation such that this system here that we have in the large phase space now becomes time independent. Now, this is the I don't want to go into the detail, but this is something that we found using this canonical transformation. You will have to introduce some auxiliary parameter rho here, and this rho is related to omega, which we had before, and a new w, which basically is the time, can be interpreted as the time independent omega of the new formulation. So now we go back and we get this Hamiltonian essentially. So you see here at the bottom, this w works like the time independent omega, and then we are good to quantize this one. So this rho actually, if you put it equal to a constant, so the time derivatives disappear. This corresponds to a time-independent background, or you want to think about it as a flat background, flat space-time background. This is used for close gravitational waves, like coming from black holes close to us and all of those things. And if you want to just look at cosmological scale, you just put rho of t based on your cosmological model. And so we are here, and then we polymer quantize things because we know how to polymer quantize time-independent oscillator. And then after that, we do another inverse of canonical transformation, which now takes us to polymer quantized version, to time-dependent polymer quantized version. And finally, we get back to the usual Hilbert space, usual phase space by doing an inverse, going to the small non-enlarged or usual phase space. And using that, we get this Hamiltonian, Okay, so this Hamiltonian is when our gravitational wave, basically these perturbations, remember, these are discrete now, and the equations of motion are ugly, and it has all sort of sign and mu, and these mu's here are the polymer scale, which sets the minimum scale of the space, if you want, or space-time, and rho is related to your cosmological model. So if you put rho equal to constant, you get flat background. If you put rho equal to some other things, you get different cosmological models. This slide doesn't matter because we went to, there are two different polymer schemes. We just use one of them, in which A is discrete, which is gravitational wave is discrete. Okay, so if we want to perturbative solve equations of motion, we get this basically perturbation for the perturbation of the A, and which is basically a kind of form for H that you saw before the gravitational wave, basically amplitude. So gravitational wave with the form of the gravitational wave. So you see that the frequency here is, first of all, is shifted in the first term. First of all, it has several higher harmonics. So sine squared times cosine, blah blah, it goes on. But in each of these, you have a shifted frequency, which is proportional to mu squared, which is proportional to basically a minimum scale squared. And obviously, that tells you that the speed of the wave is now changed, and it comes with all sort of Lorentz violation effects. Also, it tells us that the time that the waves travel over large distances, this can accumulate the effects. Actually, if you look at longer traveling gravitational waves, you see more of these effects. And these are the results plotted. So just look at the green one and the blue one. So the green and the blue here, the red one doesn't matter here. So you see that for here we have a small polymer parameter, we have a large polymer parameter, just to show you how really this thing looks if the polymer parameter is large, or you can observe this. So you see there is phase shift, and there is a change in the amplitude here, and this is sort of thing that we are hoping to at least be able to check with recent or future gravitational detectors. Also about the velocity, you see that the velocity, you can find it from the group velocity of the equation that you found before. So from this here, you can find that, and that is one is the speed of light, basically, minus some value. That value depends on your mode and also on your mu and initial value of the momentum of the wave, basically. So you see that the speed of waves are always smaller than the speed of light by this factor. And this depends on the initial momentum. So the larger momentum, the smaller the speed will be, the polymer scale, obviously, and the mode case. So essentially, if it tells us that the more energetic gravitational waves see the quantum effects more. So they're they've been affected by some frictional force, quantum gravitational force that slows them down, something like that. You can interpret that like that. Okay, so if we have a case that, so this is the case so the previous case was, as I showed you, for flat background, basically. So this happens in the flat background. If you want to have time-dependent background, FLRW background, you get here. So I don't want to go into details about this. The formula is rather kind of similar, but the function now t is now replaced by a function capital T of t, which is related to the time, with this factor rho, which is related to the cosmological model that we have. So based on that, for certain non-oscillatory rho's, so we choose rho's such that the cosmological evolution is not very chaotic. So it's a simple cosmological evolution, and you see the same effects. The amplitude is changed, the phase shift is there, the speed of the waves are different compared to the classical solution. So classical solution is the green, and you can consider the blue one that is different from that. And also, in this case, we also have the change in the speed of wave, but this change is dependent on rho, the cosmological model we have, because this t was a function of rho, if you remember here. But in general, we can say that, again, the speed of light is smaller than this, the speed of waves is smaller than the speed of light, and also that depends on an initial momentum of the wave, the polymer parameter, and also the mode k. So in all of these, you see there's Lorentz violation that can be computed based on the model. This is now going to the preliminary results. So we tried to compute something that is, we can use in actually detectors. So suppose that I have a detector with two hands, and let's call the difference between the the distance that, so originally the hand has some length L, and after gravitational wave hits it, it gets from L0 goes to L1. So the difference between L0 and L1, let's call it this chi here. And this chi can be computed obviously using the classical solutions, which is well known. You see all those graphs of LIGO and other observatories that show you the oscillations. And that is the classical version. And you can also, using our method, compute the polymer version or the effective version. So we were interested in seeing, so again, this is a preliminary work. We have to, again, take it with a grain of salt. But anyway, so we saw that if we plot them, the difference of these displacements of the hand of the detector, we get some sort of this plot, which is a modulation with these. We took some simple, values for the k, for initial values and frequency and so on and so forth. So as you see here, this should be, and this should, the largeness of this effect depends on the momentum of the gravitational wave and also on the mu. This was basically computed using the geodesic deviation. So the essence of this is that we take because we have two hands of the oscillator, of the detector. So we put one hand along the lines of one geodesic and the other line along the lines of another geodesic, and then we find that basically the geodesic deviation between these two. So, and that gives us these results. Okay, so this should be constraints here. The C's disappeared. So we also tried to do some statistical analysis on two of the gravitational wave signals, based on the results that we have, and compare them. The data that we got from them, put them in our results and see what happens. So the gravitational that you see here, they had a time delay of 1.74 seconds to reach from one observatory to another one. And so the results of so based on some prior probabilities, because these are Bayesian probabilities, so you have to have some priors. Based on priors of neutron stars, we set a sample which they had high spin values. So the blue ones, the red ones, orange ones that you see here are a sample of a neutron star. So this is basically about two neutron stars. So that are that having a spin, low spin, and the blue ones are a batch of neutron stars with high spins or having a spin. And you see that for both of them, we have, this is the probability in the y-axis, and this is the value of the epsilon mu k. If you remember, epsilon I mu k, epsilon I is the initial momentum of the wave, mu is the polymer parameter, the minimum scale of the space, if you want something related to that, and k is the mode. So you see that based on these data and very preliminary results, shows us that the value of that, the dimensionless u, should be around 0.8. Now, based on that, we can put bound on our mu. In future, we are working on that still. So this is something that we had. The next thing is constraints on, again, on this dimensionless u, epsilon mu k. And that's based on several gravitational detections of LIGO's first run. So you see all of these signals here. And this is a little bit confusing because now we have one large one bump here and one bump here. So we have to work more on that, but still you see that probability and the dimensionless polymer scale. We can't really talk about that bound anywhere here still, because there's something between 2.5 and 0.5, so both of them look kind of valid. We have to work more on that in statistical analysis. But so in general, that is how we are working on these models. So I think maybe I finished too fast. So let me go to the, so we have more time for questions. So let me go to the summary. So what I presented here was that polymer perturbations of so basically quantizing or polymer quantizing the perturbations or gravitational waves on classical FLRW background. Obviously, when we have FLRW background, we have flat background too. So if you want to talk about gravitational waves coming from cosmologically near sources, like black holes that are rotating close to us, that we can simply put our rho equal to a constant, remember in our formula, and then we have the formula for that too. Even in that case, we see that quantum gravitational effects are important and show us some difference in the waveform, in the change of velocity of the waves, and so on and so forth. And our formulation actually has this possibility that although we solve it for FLRW, we can actually expand it for other cosmological background. Not that it's needed, but well, we can do that. Now, what we did was that this was probably the first time that somebody has polymer quantized a time-dependent system in this way, the time-dependent harmonic oscillator. So we found this the canonical transformation, so that makes our system. First of all, we go to the extended phase space, then we go to the time-independent extended phase space, then polymer quantized, then we go to time-dependent extended phase space, then we go back to usual time-dependent phase space. So this is a gymnastics that we had to do to get our Hamiltonian. So as I mentioned, waveforms, frequency, and the speed of propagation are changed. And the speed of propagation is always subluminal. The higher the energy of the wave, and the higher the momentum of the wave, and the higher the mode. So I'm talking about mode is k, momentum is epsilon or e, curly e initial, and the speed basically is the speed of group speed. So in that case, the higher of all of these, it tells you that the speed of the propagation is lower. So you can get some kind of difference between different colors of the wave if you want. And the most high energy one comes slower. This has been proposed for the light also, for use like photons also from before in polymer quantization. But this is another way of it. So this definitely comes with Lorentz violation, because the speed of wave is now basically depending. So it goes 1 plus k squared plus so on and so forth. So you have mode dependent the speed. By the way, the interpretation of this is that, as I mentioned, gravitational wave actually sees the quantum regime if it sees it more if it has more energy. So the work in progress that we are currently doing, hopefully by the end of this year, at least 1 or 2 of them comes out. And you saw some of the preliminary results in this talk. One of them is the detector arm. So the detector arm was also what I showed you, was also a preliminary work. We want to make sure that to put all the constants, correctly, C, G, H bar, and everything, so to get real numerical results that can be, detected or tested by LIGO. Or we are very happy also if this theory is refuted. So anyway, either way we are happy if we can test this. So the next step that we are going to do is to study the modified power spectrum of the CMB and astrophysical objects. I mean the power spectrum of waves that coming from black holes rotating each other, or neutron stars, or these sort of things, and also from CMB, which is actually very interesting for us to if we are able to do that. And finally, and what makes this work really complete is to quantize both the background and the perturbation. So we expect our results to be some sort of semi-classical approximation to when the theory is quantized completely, background and perturbation. At the moment, the background is classical, the perturbations are quantized. So we expect that these results are not completely overruled by quantization of the background, but more modifications to the results or more due to quantum effects of the background are seen later. And again, we expect that because background has quantum properties after doing this, we see even lower speeds of the propagation, because suppose that the background, the quantized background acts as a frictional kind of background. They produce a friction on the waves. Then the higher energy or the lower wavelength the waves, they can see these small, quantum effects on the finer structure of a spacetime, and they will kind of slow down. And probably they have more signatures in them. We can describe later. Yes, so that was, I think I finished again too early. So that was my talk, and thank you. And if there are any questions, I'm ready to answer them.
So we have time for questions. Are there any questions? I don't see any questions. We're still some time. I don't see any questions. Then we thank the speaker again. Thank you.
Thank you.
Speaker Iarley Lobo, are you there?
Yeah, can you hear me?
Yeah, great. We see you and hear you. Can you share your screen?
Yeah. Okay, this is it. Can you see my screen?
Yes, we see your screen. Not yet in full screen, the slides.
Okay, but do you see my green pointer?
Yes.
Okay, so. So do you see in full screen? Can I start?
Our next speaker is Iarley Lobo from the Federal University of Paraíba, and he talks about finite Planck-scale-modified relativistic framework in Finsler geometry. So please, Iarley.
Okay, so first of all, thanks for the organization of this conference and for giving me the opportunity to talk here. This has been a very nice conference today, and also has been a very nice school in the past days. So this is a work that is being done in collaboration with Christian Pfeiffer, and we hope to have the results publicized soon. But let us move on here. So, well, the outline of this talk is, first of all, gonna give you some motivations based on some previous works in which we found some deformations of the Lorentz symmetry between the rest and the lab frames during some investigations where we actually were investigating something else, but then this came out as a subproduct. Then I'm gonna go to the actual results of this talk, which are the transformations, the form Lorentz transformations between arbitrary frames that are compatible with this first transformation here, and that are finite as well. And obviously, to have the full relativistic construction, I'm gonna show you the related composition law. And then we're gonna apply these for some cases that could be interesting and important for the decay of particles from cosmic rays, like the pion decay and the distribution of secondary particles in this kind of shower. And then I'm gonna summarize. So, well, these first motivations are the ones that we are all aware of here in this conference, but basically, as we saw right in the previous talk, we can describe, actually, we can have a, let's say, modified propagation of particles due to the interaction with a quantum space-time. And actually, this could be realized by modified dispersion relations, where the modifications are suppressed by an energy scale that is supposedly to be of the order of the Planck energy. Then one can constrain this kind of scale in order to find, in order to constrain this kind of modified dispersion relation. Usually, there are many kinds of, as you know, many kinds of constraints, many kinds of proposals for constraining these quantities. But for instance, I'm citing two here. One of them is, for instance, forbidden decays, in which one usually assumes a modified dispersion relation and considers the composition law of particles, the conservation law of energy and momentum of these particles to be undeformed, which means that one is in a Lorentz invariant violating scenario. And usually this allows one to set some constraints. I'm just mentioning because the composition law is important in this kind of constraint. And also obviously some from time delays from this race between massless particles that propagate through cosmological distances and are emitted from astrophysical sources. And also in these cases, we can analyze situations in which the Lorentz invariance is broken, is violated, or also one can analyze the mixed terms, mixed contributions, where you can have live contributions or double special relativistic contributions that has been taken into account recently. So, and then when these constraints are close to the Planck energy, one says that you are at Planck scale sensitivity, basically. So our question was, for the previous papers, is there a time-based observable that could involve massive particles that does not necessarily rely on massless particles? And actually, yes. So actually, in this paper, the lifetime of fundamental particles has been shown to be a very interesting observable that can be used to test Lorentz invariance deformation. So it's based on the violation of the CPT symmetry inspired by quantum algebras. And the contributions could be constrained if measured close to the Planck scale. So based on this, we analyzed what would be the effect on the lifetime of fundamental particles if this particle propagates through an effective spacetime that captures these kinematical properties. So as we know, the lifetime of particles constitutes a natural definition of a clock. So we extended the clock postulate to this kind of propagation in this effective spacetime. And this was a work published this year. But I'm mentioning here, but we are going further into that. So basically, we used as a model the so-called Finsler geometry, in which the Finsler metric, which is a metric of the tangent bundle, as a function is defined from the derivatives of this function, which is called the Finsler function, that is responsible for capturing these departures from a standard relativistic kinematics. And this is Paul Finsler. So this is the extension of the clock postulate. One basically has that the proper time that a massive particle experiences between two events, A and B, are given by the arc length of this particle when it propagates through a space-time, in particular through a Finsler space-time. So in order to extend this postulate, we considered as a case of study the so-called bicross product basis of the kappa Poincaré algebra. So we were just inspired by the Casimir operator of the Hamiltonian or the Hamiltonian of this kappa Poincaré algebra in the bicross product basis, where here you have the Planck length or the inverse of the Planck energy, and you have contributions here that further correct the standard relativistic dispersion relation. So we found a Finsler function. As you can see here, if L is 0, one recovers the usual Minkowski norm, Minkowski definition of proper time or of arc length. But in general, you can have some corrections. And then we found that from this definition that actually the dilated lifetime of that the laboratory measures of the decay of a particle, so the dilated lifetime of a particle is given by the lifetime of a particle as if it were at rest, plus some corrections here, where gamma is the usual velocity Lorentz factor dependent on the velocity of the particle in the lab frame. So, however, in order to compare with observations, one needs to translate between the velocity Lorentz factor to the momentum Lorentz factor, which means its dependence with the energy of the particle. So to do this, we use the definition of the momentum in terms of the Finsler function. And we found in that paper this relation between the energy, the gamma factor, and the mass of the particle. So we also here for the momentum. But in fact, we realized that this was, in fact, a transformation between the energy of the particle in its rest frame and the momentum of the particle in its rest frame to the lab frame. In fact, this transformation is given by this expression here that depends on the velocity of the particle, which is absorbed here in the velocity Lorentz factor. And well, it not only resembles the Lorentz transformations, but they are indeed deformed symmetry transformations because, in fact, by construction, the energy of the particle and the momentum of the particle, the new quantities in the lab frame, obey the modified dispersion relation. So this is, in fact, a symmetry. We are, through a deformed symmetry, connecting the mass of the particle and the energy of this particle in the lab frame. And as you can see here, you have corrections that are dominated by gamma to the fourth terms, which will constitute very interesting amplifiers for effects that are derived from these transformations. So from when we join the clock postulate and this deformed Lorentz transformation that we have just found, we find that the deformed lifetime actually in terms of the energy is written this way, where one has here a correction that grows with the third power of the energy. It should be fourth if the energy was multiplied here, but here we have the third power of the energy divided by the square of the mass. So the higher the energy, one grows massively the effect. And also for light particles, this effect should grow aggressively. So, but in any case, this kind of correction, although it has these amplifiers, is responsible to bring us close to the Planck scale if we could perform this kind of measurement at particle accelerators. Using, for instance, the muon particle, we could get close to the Planck scale. However, if one aims to diversify the analysis, for instance, considering cosmic rays or some other kind of setup, it would be interesting to have a transformation between arbitrary frames. It would be interesting to generalize this kind of construction to arbitrary frames, and also to find a composition law that completes the relativistic realization of this idea. So in fact, that's what this is part of this work in progress, in which we can simply consider the most general Lorentz symmetry that reduces to the previous case when the momentum is 0 and the energy of the particle is the mass. So with this kind of correction and the imposition of the modified dispersion relation in both frames, we find some relations between these parameters or these functions actually of the velocity that has this shape. As one can see, this A here that contains the cross terms between energy and momentum, and F as well, appear in all these expressions. So we make a choice. So this is a choice to make it null because this is an underdetermined system of equations. So we have an ambiguity here and we can make this null. And if we do this, we find this kind of transformation. So let me write it again here, because this is a transformation, a finite boost transformation, finite in the sense of the velocity, the rapidity parameter. It's a finite transformation that is connecting arbitrary frames. Here I'm working on 1+1 dimensions for simplicity. And that has very powerful amplifying factors here that grow with the fourth power in the Lorentz factor. So this is interesting because we are in fact connecting the rapidity parameter with the boost parameter with actual velocities of particles. So this way one can see that it grows with the fourth power of the Lorentz factor. And actually, we can write an infinitesimal version of it, for instance, for small velocities, and derive this kind of expression here, in which, for those already aware of what will happen, these infinitesimal boost transformations are being generated by this covector here, with this parameter v, which in fact is the one that defines the boost generator, defines the boost generator of the Poincare algebra in the bicross product basis. So this is showing a compatibility between this Finsler approach and the quantum algebraic approach, which is something that was already known for some time, but also in this paper, it has been shown that there are some ambiguities in relating these quantities. Here we find some, let's say, we find some conditions to restrict these ambiguities and, you know, have everything here on in a coherent way. So we proceed to close this this construction by writing the composition law. So actually, as you know, to preserve the vertices of the interactions, one needs to consider a deformed composition law that has nonlinearities, has nonlinear terms that can compensate the nonlinearities of the new Lorentz transformation. So in general, we can write terms like this, very general, with all kinds of terms that could emerge. And also in the most general case, one could consider a deformed Lorentz transformation of this form, in which the boost parameter here needs to have some kind of back reaction when applying in the right-hand side of this condition. This is necessary to accomplish the relativity principle, and it has been firstly found in 2006 by Majid. And also here we allow it to be applied in both entries of the deformed Lorentz transformation in order to have the most general result. And this possibility has also been raised in that paper of 2014 by Barcaroli and others, published in PRD. So in general, it will have this shape here. So here is the boost parameter that depends on P when it applies on Q, and vice versa. So when using here the parity invariant composition law, you can find very simple relations between the back reaction parameters. They should only obey this law. The general case shall come in this forthcoming paper, but here let's just focus on the parity invariant case. And then we find these very simple conditions, which we can specialize even more. For instance, for two very nice simple cases. The first one is having an invariant momentum conservation, and the second one, an invariant energy conservation. For the momentum conservation, invariant momentum conservation, we can derive, from these expressions, we can relate to the composition law parameters, and then we derive an expression like this. So we find here that the momentum is preserved, the composition of momentum is preserved, but we need to have some corrections in the energy sector. Notice that in this case, the composition law is commutative. You can change P and Q freely. the coproduct acts like this. K here is momenta P and Q. And this is the infinitesimal form of this coproduct. Also, the invariant energy we can study, and we can actually study subclasses of invariant energy conservations, in which here the correction that appears in the momentum coincides with the correction that appears from the coproduct structure of the kappa Poincare algebra in the bicross product basis. So we have a full compatibility here between those constructs, although the Finsler geometry allows to have more freedom to the choice of these quantities. So we have here, due to the, the new way of the form of the finite dispersion relation, the finite deformed Lorentz transformation, we have some back reactions on both parameters. However, at the infinitesimal level, we do not have back reaction in the second entry. We only have in the, in the second entry, we only have in the first entry, which is given by an expression like this, which coincides with previously known results. So at the infinitesimal level, things are coinciding. At the finite level, things are getting a bit different, but due to the new identification of the boost parameter. So let's apply those two pieces of informations to see how this could all mix together to give some phenomenological contributions, corrections to a kind of experiment or a kind of setup that has not been analyzed in this case until now. So for instance, just to give you an example, we consider star as representing the rest frame of a parent particle. We shall study, I didn't mention, but the decay of a particle with mass m into particles of masses m1 and m2, and here I'm writing the O+ sign to represent that we are considering a relativistic scenario. So if m is the parent particle and star is the rest frame of this parent particle, and we label I as particles 1 and 2, which are the secondaries, and we say that PL is the momentum of the parent particle in the lab frame, and V connects the frame star to the lab, we can find some corrections, some equations for the special relativistic flat normalized distribution of particles produced in this kind of decay. So each particle has this kind of distribution if it's flat, and it depends on the gamma factor, on V, on the momentum of the secondary particles in the rest frame of the parent particle. And if I use the standard Lorentz transformation, I find this kind of expression here, and then in this case, one needs to specify the momentum of the secondary particles in terms of the masses of the particles and the mass of the parent particle. And well, this flat distribution is derived from the upper and lower limits in the energies of the particles in the lab, which are given by this kind of expression. It comes from the special relativistic expression, because here I'm writing the special relativistic case, the undeformed case. And then these factors come from these, considering these this plus or minus boost parameters. So, however, if you have a deformed Lorentz transformation as the one that we have been considering in this talk, you see that there is no difference actually in the difference of energies, because the velocity, the rapidity parameter, actually only enters in this undeformed case. It does not appear here in the corrected terms. It would appear if that A that I defined in the first half of this talk was not zero. It would appear if we had crossed terms, but not having them implies that actually we find the same flat distribution of particles. So one needs to be taking care about this kind of issue. But this does not give a trivial result, because the Lorentz transformations will be different, and also the composition of particles will be deformed. So we shall have some corrections here when we try to find it. We shall not find exactly this kind of expression. So for instance, just to summarize, using the velocity Lorentz, the relation between the velocity Lorentz factor gamma and the energy of the parent particle in the rest frame, and also the modified dispersion relation, we can find this kind of correction. Then one needs to find the momenta of the secondary particle, the momentum of each of the secondary particles in the rest frame of the parent particle. So one uses the modified composition law to derive some results. So for instance, I'm gonna show you the case of an undeformed energy conservation and an undeformed momentum conservation. For simplicity, I'm assuming one of the particles as massless. So as a prototype, I'm assuming like the decay of the pion into a muon and a muon neutrino or anti-neutrino. So this is a common case in when one is studying these cosmic rays. So these showers. In this case, here the pion decays into a muon and a neutrino. Since the composition law of the undeformed momentum conservation is commutative, it doesn't matter the entry of the momentum of the particle, and we find a correction like this for the distribution, the flat normalized distribution of particles. Well, if the energy conservation is undeformed and coincides with the one from the coproduct of the Kappa-Poincare and the by cross product basis, one needs to be aware because the composition law is non-commutative. So if the neutrino comes first here, in the first entry, this shall give different results for the decays of the distribution of the decayed secondary particle. And also for if the muon is the first one in this composition law. Nevertheless, notice that these terms are governed by momentum squared and momentum to the third powers here, and they all coincide. This is due to the fact that this comes from the modified Lorentz transformation, while these other ones come from the modified composition law, but we put them here for completeness and also to fulfill the full relativistic realization. So going to summarize what we just discussed, from the Finsler function, we found a Lorentz transformation that connects the rest frame and the lab frame, the rest frame of a particle and the lab frame. We extended it to connect arbitrary frames that is compatible with algebraic considerations. Then we found the relativistic composition law and the back reaction rules. And we applied these two results, to the case of a pion decay, and we found some amplifiers that are very important when one is considering these phenomenological approaches of cosmic rays. And those can bring us close to the Planck scale, we hope so, just as the case of dilated lifetime particle accelerators had the potential to do that. We learned what's important, what's not important at the practical level, and at the theoretical level, we completed this relativistic description of these transformations. So as prospects, we shall proceed into further investigations, now considering cosmic rays actually, thanks to the network provided by this cost action. That's it. Thank you very much.
Hello. We have time for questions. Are there any questions? Jose Manuel.
Which is the order of the band you can put on or its inverse to have in GSK with these particle physics experiments?
I am sorry, I couldn't hear. Let me see if I can move to what kind of bounds one can.
Can you hear us better now?
Yes, I can hear you.
Okay.
yeah, which is the order of the bounds you can put on L, that is on the high energy scale, the inverse, no, the high energy scale, with this particle physics experiment studying the decay of the pion.
Yeah, I mean, so let me just recall the case of the muon, because that's important. In this case, it's important to have this balance between the available relative uncertainties in the experiments and the energy of the particles considered. So in the case of the muon, if we could have done this kind of experiment in a way that is as precise as it is done for low energy muons, we could, at optimal conditions, we could be already exactly at the Planck scale. However, these are super optimistic conditions, but in any case, we wouldn't be so far from the Planck scale, maybe some 2 orders or something like that. In the case of the muons, of the pions, the masses are similar, are of the order of 100 MeV, right? And of the case of the muon, but the energies, as far as I know, are not, I mean, for this specific case, are not as powerful as was the case of of those muons or of those, let's say, parent particles in LHC, let's say. So because, I mean, you start to lose energy once the shower enters the atmosphere. So, I mean, despite this first jet is very energetic, up to 10 to 19, 10 to 20 GeV, I expect that the energy of the pion is not so high. So, but in any case, even if it approaches like some GeV, 100 GeV or something like that, we show, I mean, it depends on the sensitivity of these experiments that are based on this kind of observer. So, but as from preliminary conversations with other members of the action, we seem to be a few orders of magnitude from the Planck scale, but nevertheless, there is room for improvement in the next years. So, I mean, this is like a midterm, maybe long-term kind of bet of having this new observable with the potential to reach the Planck scale.
Okay, thank you. Are there further questions? I don't see any questions, so thank you again, Iarley, for the very nice talk.
Thank you.
And with this, we conclude our session and our first day of the second annual conference of our cost action. So thank all the speakers of the day again. And the next event is the reception in the town. So thank you. We have to be there before 8, and also bring your vaccination certificate or negative test. Yeah, and otherwise, see you later for the reception or tomorrow.